We go now to analyze the third of these integrals, this one here. And we have to prove that this is convergent for any s in this region, which is the equivalent to saying that is convergent for any possible value of x, because if s is larger than 1 or smaller than -1, this integral is not defined in some points of this interval here. The reason is, suppose that you take 0, this function here at 0, so you have the cosine of 0 is equal to 1, but if s is larger than 1, then the denominator would be 1 minus s, and this would be a negative number. So we would have here the logarithm of a negative number, which is impossible. So that means that there would be an angle which is larger than 0, for which beyond which this function would not be defined. Okay, so the only possibility for this function to be defined everywhere in the interval 0 pi half is that the absolute value of s is smaller than or equal to 1, which means that s is between -1 and 1. Okay? All right. So we're going to separate out two cases. The first case is when s is strictly larger than -1 and strictly smaller than 1. All right? Because in those two cases, neither this or this is ever 0, right? Even when the cosine takes the largest value, right, here, which is 0, right? 1, when x is equal to 0, then this number here would be 1 minus s, which is a strictly positive number. And there's no problem in evaluating the logarithm. So for any s in this interval, this is a perfectly well-defined and continuous function everywhere here in 0 pi half. However, there is a cosine here. And the cosine vanishes when pi is equal to 2, when x is equal to pi half, right? However, if you put here pi half, this is 0, this is 0, and the logarithm of 1 is also 0, so you have actually 0 divided by 0. So we have no idea whether this function behaves well or not at this limit here. So let's see, how do we handle that? Well, we can split this logarithm in two, right, like this, using the properties of the logarithm. The logarithm of a quotient is the difference of logarithms. Okay, so we have that. Now, when x goes to pi half, the cosine goes to 0, which means that we can use this expansion for the logarithm. Is u plus ou, right? And if we substitute, if we substitute u by minus u, what we have is minus u plus ou. This is when u goes to 0 in both cases, right? Okay, if we subtract, then we have that the logarithm of 1 plus u over 1 minus u, that means the difference between these two logarithms, this is u minus u is 2u plus ou when u goes to 0. Okay, so this function behaves just as 2 times the argument here. Now the argument in our case is s cosine x, and the limit is when x goes to pi half, which is when this argument here goes to 0. So the logarithm of 1 plus x cosine over 1 minus s cosine, this is equal to 2 times s cosine plus o cosine x when x goes to pi half. Right? Because as I said, when x goes to pi half, the cosine, s cosine goes to 0. All right? So we have the behavior of this function very near pi half. And it behaves just proportional to the cosine, which is very good because now the logarithm of 1 plus x cosine over 1 minus x cosine divided by cosine is just 2s plus 1 when x goes to pi half. And now we know that the behavior of this function is perfectly smooth. So this function is continuous when x goes to pi half, so there's no problem. So this function is not singular, it's just an ordinary function, well-behaved function in a finite interval. So we just have to perform a Riemann integral, and that's it. So when s is in this range, the integral is normal, it's not even improper, right? Okay, so the problem may be then when s is equal to plus or minus 1. And of course, the logarithm of, well, for s equal to 1, you have this, for s equal to 1, you have this, and here you have 1 minus cosine x, okay? And this is equal to minus the logarithm of the reciprocal of this, this fraction, which is this. This is the case when s is equal to 1. This is the expression of the function when s is equal to -1. So actually, the two arguments are basically the same except for just one sign. So that means that we need only to analyze one case. We're going to analyze this one, and we have the answer for both. Whatever happens for this one also happens for the other one. So we actually have to prove that the integral from 0 to pi half of the logarithm of 1 plus cosine x over 1 minus cosine x dx over cosine x, this is a convergent integral, right? Okay, there's no problem at pi half. We are in exactly the same situation. With this is valid for every s, even if we put s equal to 1 or minus 1, this is still well behaved, right? So it's proportional to s, okay? So it's valid even for this case. So that means that at pi half, there's no problem with this function. The only problem is at 0. And it is a problem because for x equal to 0, here we don't have any problem anymore because the cosine of 0 is just 1, right? But here we do have a problem because in the denominator we have 1 minus 1, 0, and we have the logarithm of a 0, right? Well, actually the logarithm of infinity, okay, but that is a problem, right? All right, we can separate out this integral in two, right? So we have on the one hand the integral of from 0 to pi half of the logarithm of 1 plus cosine x dx over cosine x, okay? This function has no problem whatsoever, right? In this interval 0 pi half, the cosine is always positive, goes from 1 to 0. So this integral goes from 2 to 1. The argument of the logarithm, sorry, goes from 2 to 1. So this behaves perfectly well, and so does the cosine here. As I said, well, even when x is close to pi half, well, as we have analyzed before, it's not exactly this, but the analysis is identical. This function behaves perfectly well, right? But the other one, the other integral, it is a problem. Okay, this integral here is a problem, right? And not because of the cosine here, and not because of the limit pi half, but because of the limit at 0, because then the argument here is 0, right? So let's focus on this integral here and see what we can say about that. Well, what can we say about this integral? We can say that the argument here, 1 minus cosine x, well, actually, when x goes to 0, the cosine of x is equal to 1 minus x squared over 2 plus x4 over 24 plus x4 when x goes to 0, right? And that means that 1 minus cosine x is equal to x squared divided by 2 times 1 plus, I'm just factoring out this factor, so I have x squared here, and I have 12 here plus x squared when x goes to 0, right? Okay, so we have this. So now we take the logarithm of this, and then we have the logarithm of 1 minus cosine of x, and that is equal to the logarithm of this, which is the logarithm of x squared half plus the logarithm of the rest, the logarithm of 1 plus x squared divided by 12 plus x squared. Okay, now this first one is minus the logarithm of 2, because 2 is in the denominator, right? But that is a constant, this is no problem, plus 2 times the logarithm of x. And this is the problematic function, right? This is the problematic function, because the argument is 0 when x is 0. And then we have this other one here, but we can, the argument here goes to 0 when x goes to 0. So we can just use the expansion of the logarithm and write that this is x squared over 12 plus ox squared when x goes to 0. No problem with this one. This is just a polynomial. So the only problem is with this function here. So we have to analyze what happens with the integral from 0 to pi half of the logarithm of x. But actually we've done this before. The logarithm, well, we write this as the limit when epsilon goes to 0 plus of the integral from epsilon to pi half. Well, the fact that this pi half is irrelevant. It could be any other number. And then we have the logarithm of x dx, but we know a primitive of that, which is just x log x minus x. So we substitute this at epsilon and pi half there. Well, then you have pi half log pi half minus pi half, just a constant, minus epsilon log epsilon plus epsilon. And of course this goes to, well, the limit of this is equal to the limit of this. Of course, epsilon goes to 0 plus, right? This is a constant, this goes to 0, this goes to 0, so actually it's just a constant, so it's well behaved, right? So the integral is finite. Okay, the integral of this integral here is equal to, well, minus logarithm of 2 times the length of the interval, no problem, plus an integral that is of a function that is well behaved, no problem, this will give you a number, whatever, and then this integral here, which also deals a finite value here. So this integral converges. So we see that the integral at the end of the day converges for every value of s. For s strictly between -1 and 1, because then the function is not even this is not even an improper integral, and even when s is 1 or -1, because then the function has a primitive that has a well-defined limit when epsilon goes to 0, and then the integral converges.